Okay, so we continue chapter 4 by example 4.1.9 of the book, which basically shows a disproof of an existential statement. So here is the existential statement that we are going to prove that is false. It says there is a positive integer n such that n squared plus 3n plus 2 is prime. So in order to solve this, we are going to first find the negation of this statement. So since this statement is an existential statement because it starts with there is, the negation of this statement is this: for all positive integers, n squared plus 3n plus 2 is not prime. So in order to prove that the existential statement is false, we just need to prove that this universal statement is true, because this is the negation of that existential statement. So if the existential statement is false, this universal statement must be true. So we are going to prove that for all positive integers n squared plus 3n plus 2 is not prime. So in order to prove that, we first factor n squared plus 3n plus 2 to obtain this. So n squared plus 3n plus 2 is multiplication of n plus 1 and n plus 2. So we also note that n plus 1 and n plus 2 are integers because they are sum of integers. That's why they are integers. And then both n plus 1 and n plus 2 are greater than 1 because n is a positive integer. So by adding 1 and 2 to a positive integer, the number that you get is greater than 1. So we conclude that n squared plus 3n plus 2 is a product of two integers, each greater than 1. And based on the definition of prime numbers, we conclude that n squared plus 3n plus 2 is not prime. So we prove that for all positive integers, n squared plus 3n plus 2 is not prime. And as a result, we prove that the existential statement, the original existential statement that we said at the beginning, is false, because the existential statement is the negation of what we prove to be true. Okay, so we continue chapter 4 by defining a rational number. We say a real number R is rational if and only if it can be exposed as a quotient of two integers with a non-zero denominator. Okay, so in a formal way we can say R is rational if and only if there exist two integers a and b such that R can be written as a divided by b, and b should not be equal to 0. B should be non-zero because b is the denominator. So this is the definition. Now let's use this definition to solve example 4.2.1 of the book, which basically wants us to determine if any of these numbers that you see are rational or not. The first one is negative 5 over 39, and the answer is yes, because minus or negative 5 over 39 is a quotient of integers negative 5 and 39. So based on the definition of rational numbers, this number is rational. The second number is 0.281, and if you look at this number, this can be written as 281 over 1000. And since both 281 and 1000 are, integers, and 1000 is not equal to 0, so based on the definition of rational numbers, we conclude that this number is also a rational number. The next one is 7. So 7 can be written as 7 over 1, and obviously it's a rational number. How about 0? 0 is also can be written as 0 over 1 or 0 over any other integer which is not 0. And obviously, since the denominator is not 0 and both numerator and denominator are integers, so 0 becomes a rational number. Part E is a little bit harder to prove. It says x is equal to 0.121212, and the digits 1 and 2 are assumed to repeat forever. So consider this number as x, okay? So we conclude that 100x would be equal to 12.121212 and repetition of 12 forever. By subtracting x from 100x, we get 12.121212 minus 0.121212. So the fractional part of these two numbers will cancel out each other, and then we'll get 12 at the end. So we prove that 100x minus x, which is 99x, is equal to 12. So by dividing both sides of this equation by 99, we conclude that x is 12 over 99. So x is a ratio of two non-zero integers, and as a result, it's a rational number. The last part of this example is if m and n are integers and neither m nor n is 0, then prove that m plus n over mn is a rational number. So to prove this, we say since m and n are integers, so both m plus n and mn are integers because set of integers are closed under summation operation and multiplication operation. So m plus n becomes integer and m times n becomes integer. Also, since neither m nor n are 0, so m times n is not equal to 0 because of zero product property that you see here. This is the zero product property. It says if neither of two real numbers is 0, then the product is also not 0. So we consider this property as a fact, and we are not going to prove this, but just keep in your mind that if you have two real numbers and none of them are 0, then their product will not be 0. So this can be equivalent of its contrapositive. So the contrapositive of this zero product property says if the product is 0, the product of two real numbers are 0, then either the first one is 0 or the second one is 0. So since we have this property true, then its contrapositive is true too. Okay, and as I said, we are not going to prove this property. We consider it to be true. So as a result, mn is not equal to 0. So the denominator of this number is not 0, and both the numerator and denominator are integers. So we are done with the proof. Next, we see theorem 4.2.2 of the book, which says the sum of any two rational numbers is rational. In order to prove this, suppose R and S be two rational numbers, and we are going to show that R plus S is rational, so that we prove the theorem 4.2.2. So since R and S are both rational, you can write R and S in this form. R can be A divided by B, and S can be written as C divided by D, where A, B, C, and D are all integers, and B and D are non-zero, right? Because B and D are the denominators of these two fractions. So R plus S becomes A divided by B plus C divided by D, because we are going to substitute R and S with the respective values. So by basic algebra, we can conclude that A over B plus C over D is equal to this number, which is the denominator is AD plus BC, and the denominator is B times D. So let P be the denominator of this number, which is AD plus BC, and let Q be the denominator, which is B times D. So P and Q are integers because, as I said before, the set of integers are closed under summation and multiplication, right? So AD plus BC is integer, and BD is also an integer because B and D are both integers. Also, we need to prove that Q, which is the denominator, is not zero. Based on the zero product property that we saw before, we can conclude that since B and D are not zero, so their multiplication also becomes non-zero. So Q is not zero, and as a result, since R plus S can be written as P over Q, and P and Q are integers, and Q is non-zero, we can conclude that R plus S is rational by the definition of rational numbers. So we showed that if R and S are rational numbers, then R plus S becomes rational. So we are done with the proof of theorem 4.2.2. Okay, so we continue chapter 4 by the following definition. We say if n and d are integers and d is not zero, then n is divisible by d if and only if n equals d times some integer. Instead of n is divisible by d, we can say that n is a multiple of d, or d is a factor of n, or d is a divisor of n, or d divides n. Any of these four phrases are equivalent to saying n is divisible by d. And here is the formal notation. We write d divides n. So symbolically, if n and d are integers and d is non-zero, then we can say d divides n if and only if there is some integer k such that n is equal to d times k, right? That's the formal definition of n is divisible by d. Now, let's look at the contrapositive of this definition. So you know that the contrapositive of P then Q is not Q then not P, and based on what we said before, we know that the contrapositive of a conditional statement is equivalent to that statement. So since the definition is obviously true, I'm going to write the contrapositive of the definition, and obviously it should be true, right? So here is the contrapositive of the definition. We say for all integers n and d, if d does not divide n, then So if the first part is false, then the second part becomes false, and vice versa. So here is the negation of the second part. The second part in the definition is an existential statement, right? It says there exists some integer k such that n is equal to dk. Now the negation of that becomes a universal statement in this form. We say for every integer k, n cannot be written as d times k, or n over d is not equal to k, which the whole thing is equivalent to saying n over d is not an integer, right? Because n over d is not equal to k for every integer k, so n over d cannot be an integer, right? So basically what we got is this. We say n does not divide d does not divide n if and only if n over d is not an integer. So that's the contrapositive of the definition, and obviously it is true. So we don't need to prove this anymore because, as I said, the contrapositive of a true statement is true. Okay, so as an example, let's consider the following statements, and let's verify that first 21 is divisible by 3. Here is how we verify it. We say yes, because 21 is equal to 3 times 7. So there is an integer k such that 21 is equal to 3 times k, and we are done with the proof. The second one is, does 5 divide 40? Yes, because 40 is equal to 5 times 8. So 8 is that integer that exists. In part C, we are asked to see if 7 divides 42, and yes, because 42 is 7 times 6, then is 32 a multiple of negative 16? Yes, because 32 is negative 16 times negative 2. So k in this example is negative 2. So obviously k can be positive or negative. Then we have, is 6 a factor of 54? And the answer is yes, because 54 can be written as 6 times 9. And the last one is 7 a factor of negative 7? Yes, because negative 7 can be written as 7 times negative 1. Again, in this example, k is negative 1. Another example is example 4.3.2 of the book, which wants us to find the divisors of 0. If k is any non-zero integer, does k divide 0? And the solution is yes, because 0 can be written as k times 0, right? So any non-zero integer divides 0. That's the conclusion. Next, we prove the theorem 4.3.1 of the book, which basically says for all integers a and b, if a and b are positive and a divides b, then a should be less than or equal than b. In order to prove this, we need to use the definition of divisibility. We say, suppose a and b are positive integers and a divides b. That's the assumption, right? So we need to show that a is less than or equal to b. That's the conclusion of the theorem. So since a divides b, then there exists an integer k so that b is equal to a times k, right? And then since both a and b are positive, k must be positive. Okay, so what we got here is b is equal to a times k, and k is positive because both a and b are positive. Now, since k is positive and k is integer, So k should be greater than or equal 1, right? Because the smallest positive integer is 1. So k cannot be less than 1. So k is either 1 or greater than 1. So k is greater than or equal to 1. Then by multiplying both sides of this inequality, we get by multiplying the both sides of this inequality by a, we gives us this inequality. We get a is less than or equal to ka, because a times 1 is a and a times k is ka, right? So a is less than or equal ka, where ka was b based on what we got here, based on the definition of divisibility. We got b is equal to ak, right? So we conclude that a is less than ka, and since ka is b, we get the inequality that we want. We get a is less than or equal b, right? So we are done with the proof. Now let's look at the example 4.3.7, which says, is the following statement true or false? Here is the statement. For all integers a and b, if a divides b and b divides a, then a is equal to b. You want to check if this statement is true or false, right? I'm going to claim that this statement is false, and to prove my claim, I need to find the counterexample, right? Because this is a universal statement, because it's just for all integers, right? So if you want to disprove a universal statement, you have to find a counterexample. My counterexample is this: a is 2, b is negative 2. Okay, you could say any other integer like 5 and negative 5, or negative 7 and 7. The only property that they should have is a should be negative b. Okay, a should be equal to negative b. So let's see how we continue with this counterexample. Okay, so a divides b, that's true, right? Because 2 divides negative 2, because 2 is equal to negative 2 times negative 1. And similarly, b divides a, because negative 2 again divides 2, right? But obviously, a and b are not equal. A is 2, b is negative 2. As a result, we prove that this statement is false because we found a counterexample. Another topic that we talk about in chapter 4 is proof by division into cases. If you remember, when I was introducing different types of arguments, I said one of them is proof by division into cases, and I said in that part, I said we have only 2 cases, and then I said the argument. But here we may have as many as n, but n is any number greater than or equal to cases, right? So we have n cases, a1, a2, all the way to an, and we know that one of these n cases is true, or a few of them are true, but at least one of them is true. Okay, we know as a fact that either a1 is true or a2 is true, all the way to an is true. Then we know these n conditional statements. The first one is if a1, then c. The second one is if a2, then c, all the way to if an, then c. So when we have all of these n conditional statements, we can conclude that c must be true, regardless of which of a1, a2, all the way to an happens. Okay, so let's see this theorem 4.4.2 of the book, and let's see how we can prove this using the method of proof by division into cases. The theorem is called the parity property. Any two consecutive integers have opposite parity. So let's prove this. We know that we have two consecutive integers. So two consecutive integers are given, right? For example, m and m plus 1. Since the integers are consecutive, so if one of them is n, the next one should be m plus 1, right? And what we need to show is that if m is even, then m plus 1 must be odd, and if m plus 1 is even, then m must be odd, because they should have opposite parity, right? So we must show that one of m and m plus 1 is even and the other one is odd, right? So by the parity property, either m is even or m is odd, right? We have only two cases. The first case is m is even, the second case is m is odd. There's no other cases, right? So here we use the method of proof by division into cases. We break the proof into two cases depending on whether m is even or odd. In the first case, we say m is even. Okay, so based on the definition of even numbers, m is equal to 2k for some integer k, and as a result, m plus 1 becomes 2k plus 1, right? Which is odd based on the definition of odd numbers. So in the first case, to prove that if m is even, then m plus 1 becomes odd, and as a result, two consecutive integers have opposite parity. So we prove the conclusion for the first case, but we are not done yet, because there are two cases, either m is even or m is odd. So we are halfway through the proof, but we are going to prove the next half, right? The next half of the proof says, in the case 2, m is odd, okay? So if m is odd, based on the definition of odd numbers, m is equal to 2k plus 1 for some integer k, and as a result, m plus 1 becomes 2k plus 1, which is m, plus another one. So this is the value of m plus 1, which is 2k plus 2, and by factoring out the 2, we get 2 times k plus 1. Okay, obviously k plus 1 is an integer, right? Because it's the summation of k, which was an integer, and 1, which is an integer. So k plus 1 is an integer, and so we prove that m plus 1 is equal to 2 times k plus 1, where k plus 1 is an integer. So based on the definition of even numbers, m plus 1 is an even number because it is equal to twice some integer. And as a result, m plus 1 is even. So m was odd, then we prove that m plus 1 is even. So again, we conclude that any two consecutive integers have opposite parity in the second case. So if the first case was true, we proved the conclusion. If the second case is true, then we prove that the conclusion is true, which is the two consecutive integers have opposite parity. So we can claim that we proved theorem 4.4.2 by the method of proof by division into two cases. So that's the proof. It is a very strong method of proof. We can use it in many different occasions when we are going to prove something. So keep in mind, this method is very, very powerful, and it's very helpful for many different proofs. Okay, the next part, we define an absolute value for x. Okay, an absolute value of x, which is denoted by this symbol, is defined as follows. We say absolute value of x is x if x is greater than or equals 0, and negative x if x is less than 0. Okay, now let's prove lemma 4.4.4 using the method of proof by division into cases. Here is the lemma. It says for all real numbers R should satisfy this inequality. Basically, R should be less than or equal the absolute value and should be greater than or equal the negative of absolute value. And here is the proof. We say since R is a real number, we can divide the problem into two cases. The first case is R is greater than or equals 0. The second case is R is less than 0. So since R is a real number, either it is negative or non-negative. The first case is that we assume R is non-negative. R is greater than or equals 0. In this case, based on the definition of absolute value, the absolute value of R is equal to R, right? And since R is positive and negative, the absolute value is negative, obviously R is greater than negative the absolute value, because any positive integer or any positive real number is greater than any negative real number. So as a result, we prove the inequalities. We prove that R is greater than or equal to negative the absolute value and is less than or equal the absolute value. So the first case is done. Now let's go to the second case. The second case is R is negative. Let's see if we can prove the lemma in the second case. In the second case, by the definition of absolute value, again, we say the absolute value of R should be negative R, because as you see here, we said the negative value of x is negative x if x is negative. In this case, R is negative, so absolute value of R is negative R. Now by multiplying both sides by -1, it gives us R is equal to negative R. The absolute value of R. Also, since R is negative and absolute value of R is positive, and any negative number is smaller than a positive number, so R is less than the absolute value of R. So again, in this case, we also reach to the the inequality that we were looking for. R is less than or equal the absolute value, and R is greater than or equal the negative absolute value. So in both cases, we reach to the conclusion. As a result, in all cases, we have this inequality. Okay, so another lemma 4.4.5. For all real numbers R, the absolute value of negative R is equal to the absolute value of R. Let's prove it again by the method of proof by division into cases. In this example, we have three cases. The first case is negative R is positive. The second case is negative R is 0. And the third case is negative R is negative, right? Because negative R is also a real number, and any real number is either positive or negative or 0, right? So negative R has also these three cases. If negative R is positive, then by definition of the absolute value of negative R becomes equal to negative R. If negative R is 0, again by the definition of absolute value, the absolute value of negative R is negative R. And in the third case, the absolute value is negative of negative R. Okay, So let's simplify this. When we say negative r is positive, we mean r is negative, right? If negative r is 0, means r is 0. And if negative r is negative, means r is positive, right? These are basic algebra, so I'm not going to go to the details of it. And here, if you see, if negative r is 0, then negative r becomes 0, right? So I just wrote 0 instead of negative r. And since negative r is r, I just simply replace this by an r. So we reach to the definition of an absolute value. We basically found this one, which is actually the definition of absolute value of r. So we are done with the proof of lemma 4.4.5. And finally, we proved theorem 4.4.6, which is actually a very, very popular theorem, which is called the triangular inequality. It basically says for all real numbers x and y, the absolute value of x plus y is less than or equal to the absolute value of x plus the absolute value of y. We are going to prove this inequality. To do this, again, we are going to use the method of proof by division into cases. We say we have two cases. Either x plus y is non-negative or x plus y is negative, right? Because x and y are real numbers, so x plus y is also a real number, and any real number is either negative or non-negative. In the first case, where x plus y is non-negative, we can say x plus y is equal to its absolute value based on the definition of absolute value, and based on the lemma 4.4.4, which we proved, we can say x is less than or equal to the absolute value of x, and y is less than or equal to the absolute value of x. And then by adding both sides of these inequalities, these two inequalities, by adding both parts of both sides of these two inequalities, we get x plus y is less than or equal to the absolute value of x plus absolute value of y. So as a result, since we have this equation, we will obtain the inequality that we were looking for, which is absolute value of x plus y is less than or equal to the absolute value of x plus absolute value of y. Now let's look at the second case. In the second case, x plus y is negative, so by the definition of absolute value, we obtain that the absolute value of x plus y is negative x plus y, which is equal to negative x plus negative y. And so based on lemma 4.4.4 and 4.4.5 that we proved before, we find that negative x is less than or equal to the absolute value of negative x. That's based on the previous lemma, lemma 4.4.5. And the absolute value of negative x is basically equal to the absolute value of x. Again, we have the same reasoning for negative y. Negative y is less than or equal to its absolute value, and absolute value of negative y is equal to the absolute value of y. And now we combine this equation and these two inequalities to obtain this new inequality. we say the absolute value of x plus y is equal to negative x plus negative y based on this equation. And by combining these two inequalities, we get negative x is less than the absolute value of x less than or equal. And negative y is less than or equal the absolute value of y. And we are done with the proof because we reach to what we are looking for, what we were looking for. So in both cases, we reach to the inequality that is called the triangular inequality. So we are done with the proof.